Look around. The air is filled with an invisible, chaotic web of signals. Hardware and software from a dozen different manufacturers have to somehow take a video file from a massive server rack and play it perfectly on your mobile phone. But a server built by one company doesn't naturally speak the same language as a phone built by another. If they don't agree on a specific set of rules to package and send that data, it's just digital noise. This diagram shows the two primary ways to solve this. On the left is the OSI model, which looks like a highly detailed 7-story architectural blueprint. On the right is the TCP/IP model, acting more like a sturdy, utilitarian 4-story building. One gives you perfect theoretical detail, while the other is what the actual internet is built out of. If you're building a career in IT, you have to decide which one of these frameworks demands your focus. Understanding which one to prioritize depends entirely on whether you are designing the theoretical structure of a system or trying to make a physical network actually run. To understand why we have two models, we have to look back to the 1970s. The U.S. Department of Defense needed a way to build resilient networks that could survive physical damage, a project that started with ARPANET. Researchers at places like UCLA weren't simply trying to write perfect theory. They were in the trenches, trying to force a concept called packet switching to work across unreliable physical lines. As they connected different networks together, researchers like Vint Cerf and Bob Kahn at Stanford drafted the rules that actually got the data from point A to point B. This became the Transmission Control Protocol and the Internet Protocol. While those teams were wiring up working networks, an international standards organization took a step back. They spent years designing the OSI model, an idealized, comprehensive framework meant to map out every possible step of network communication. By the time the OSI model was finished and heavily backed by European governments, TCP/IP was already scaling globally. The internet was running on TCP/IP. OSI, with its strict rules, was simply too heavy to deploy efficiently. So TCP/IP became the tool we used to build because it survived the implementation war. But OSI survived because it offers a perfect, granular language to describe what's happening inside the wires. Let's look at the OSI model first. Think of it as the architect's blueprint. It breaks the chaotic process of network communication into 7 highly specific, isolated steps. Looking at this 7-tier pyramid, the bottom 3 layers form the hardware foundation: physical, data link, and network. This is where your raw cables connect, where MAC addresses verify local hardware, and where IP addresses handle the routing. Moving up to layer 4, you find the transport layer. This is the heart of the model, dedicated entirely to end-to-end communication, making sure your data arrives in the right sequence without errors. Finally, the top 3 layers, session, presentation, and application, handle the software side. They maintain the open connection, format and encrypt the data, and provide the interface your web browser interacts with. Breaking communication into 7 pieces gives engineers a universal vocabulary. If something breaks, you don't have to guess. You can isolate the failure to an exact functional layer. For instance, a cybersecurity analyst will treat a layer 2 attack, like someone spoofing a MAC address on a local switch, very differently than a layer 7 attack, like a SQL injection hitting a web application. The map tells you exactly where the fire is, but that strict separation has a cost. Forcing every piece of data to travel through 7 distinct checkpoints is rigid. It demands a level of abstraction that bogs down fast, efficient software development. This granular separation makes OSI the standard tool for troubleshooting, even though it adds significant complexity compared to models designed for rapid deployment. That brings us to the TCP/IP model. These are the builder's tools. This is the streamlined operational framework that practically all modern networking actually runs on. As you can see in this 4-tier structure, TCP/IP simplifies things. The wide foundational block is the network access layer. It merges the physical hardware and the data linking protocols into one unified category. One step up is the internet layer. Its sole responsibility is logical IP addressing and finding the best path to route packets across different networks. Above that is the transport layer. This is where core protocols take over. You use TCP when you need reliable, ordered delivery, like loading a web page. You use UDP when you need fast, connectionless streaming, like a video call. Finally, the massive top block is the application layer. It takes all the high-level software, session management, and formatting functions and consolidates them into a single operational space. Compressing 7 layers down to 4 makes TCP/IP highly scalable and much easier to deploy. But the trade-off is that it blurs the precise lines you sometimes need for deep, complex troubleshooting. TCP/IP runs the world today because, in the early days of the internet, practical scalability and proven protocols mattered more than theoretical perfection. When we put them in a side-by-side comparison matrix, the relationship becomes clear. On the left, OSI's top 3 layers, application, presentation, and session, funnel directly into TCP/IP's single application layer on the right. The transport layers align perfectly across both models. And OSI's network layer corresponds exactly to TCP/IP's internet layer. Finally, OSI's bottom 2 layers, data link and physical, are compressed into TCP/IP's single network access layer. This mapping illustrates that OSI draws strict boundaries for analysis, while TCP/IP merges those boundaries for the sake of speed. These models act as 2 distinct lenses for viewing the exact same data transmission, chosen based on the goals of the engineer. So how do IT professionals know which framework to leverage? This scorecard maps out exactly where you should focus, depending on your role. If you are a student, an educator, or studying for a certification, prioritize the OSI model. You need it to pass industry exams, and it provides the foundational concepts required to truly understand how data encapsulation works. If you are a network administrator or an architect, your focus is TCP/IP. When you configure a firewall, set up a subnet, or manage daily routing operations, you are working directly within the TCP/IP protocol suite. And if you are a cybersecurity analyst or an advanced troubleshooter, you have to use both. You use TCP/IP to observe the actual network traffic flowing through your systems, and you use OSI to precisely pinpoint the structural location of an incoming attack. Your daily task dictates your primary tool, but true expertise requires fluency in both frameworks. TCP/IP is the practical engine we use to build our networks. OSI is the theoretical map we use to analyze and teach them. The most capable networking professionals don't choose one over the other. They become dual-stack experts, building with the rugged scalability of TCP/IP and troubleshooting with the surgical precision of OSI.